So I'll come back to this contention based MAC. So previous all these things, MACA, MACA-W, they were contention based MAC. What was the problem in contention based MAC? They were not having any reservation mechanism. They were not having any reservation mechanism means the reservation of bandwidth, reservation of time slot was not being done from the transmitter node to the receiver node for the MACA and MACA-W thing. Hence, there was no guarantee that quality of service will be maintained in case of MACA and MACA-W. Though MACA-W is very advanced, but then also due to the mobility of the node, there can be node link break at any time. That means if there is very important voice communication is going on, real-time voice communication by the ad hoc network by using MACA-W, not possible because MACA-W is not using any kind of reservation mechanism. What is meant by reservation mechanism here? Before the transmission takes place, and reservation mechanism is mainly for live real-time data traffic, voice traffic. For data traffic, MACA and MACA-W can do, but for voice traffic, MACA and MACA-W cannot do, because voice traffic is very important. Data traffic, 1-2 packet drop, again retransmission of data you can do, but real-time voice traffic, it cannot accept any kind of packet drop or link breakage or those kind of thing. So difference between contention based MAC and contention based MAC with reservation. First and foremost difference we have already discussed, that contention based MAC like MACA and MACA-W, they are used only for data transmission, not for voice transmission. But this today's topic, contention based MAC with reservation, they can be used for both, mainly for voice traffic and for data traffic as well. Because contention based MAC with reservation, they are ensuring quality of service. What is meant by quality of service? Data will surely reach to the receiver within the time and unaltered. Whenever the data is reaching from transmitter to the receiver, there will not be packet drop, and data will be must reach to the receiver without any kind of problem, without any kind of noise, without any kind of drop in the packet. So there are three techniques that we have discussed here in contention based MAC with reservation. Okay, the first characteristics protocol is called as distributed packet reservation multiple access protocol. So here it is shown, distributed packet reservation multiple access protocol. In short, it is called as D-PRMA. Okay. So before that, first let us know what is PRMA. Okay, so protocol PRMA is a protocol. Okay, so PRMA full form is packet reservation multiple access protocol. In PRMA protocol, what we are doing is, in PRMA protocol, first bandwidth reservation is occurring, then the contention occurs. Contention means fight. All the sender nodes, they are fighting for the channel. Okay, so first bandwidth reservation occurs for all the sender nodes, and then the contention happens. Whichever node wins the contention, whichever sender node wins the contention, all the bandwidth will be reserved to that sender node, and from that sender to the receiver, the bandwidth will be fixed, the route path will be fixed, and quality of service is always provided for real-time data traffic. So voice can be a real-time data traffic. But this PRMA is whenever it is applied in distributed manner. So what is meant by distributed? We have found that ad hoc sensor network or ad hoc network is a distributed network because there is no central control. Okay, cellular network is a central controlled network. Cellular network is a not a distributed, it is a centralized control network. So whenever this centralized control PRMA, that is packet reservation multiple access protocol, is applied for ad hoc wireless network, then it is called as D-PRMA. So this distributed word is very important. Distributed means distributed control. So there is no centralized control. So this is the first thing we learned in case of ad hoc, that is ad hoc is not having any centralized control. Ad hoc is all distributed, and in a distributed manner, all the nodes keep on talking to each other and they control the data flow in the whole network. Okay, so PRMA is a mechanism where bandwidth is reserved. When the same PRMA is applied for ad hoc, it is called as distributed PRMA. So extended version of PRMA into distributed network, that is ad hoc network device for ADWSN. So distributed packet reservation multiple access, in short form D-PRMA, is a protocol which is providing voice support in ad hoc wireless sensor network. So generally PRMA can produce, PRMA can provide the voice support, but whenever this PRMA is being applied for ad hoc, then it is called as D-PRMA. So this D word is for distributed. And because of this D-PRMA, we can have, which is a TDMA based, that is time division multiple access. Because of this D-PRMA, we can have voice transmission over ad hoc wireless network. See, initially ad hoc wireless network was there just for data transmission, sensed whatever sensed data from sensors, whatever we were getting, that was transmitted for critical application, military application, disaster management application and all. Later on, people started thinking, why not internet over ad hoc wireless network? Why not voice over ad hoc wireless network? So all this thing kept on coming later on. Okay, so for voice over ad hoc wireless network, we cannot use MACA or MACA-W. For a voice over ad hoc wireless network, we have to use some kind of contention based protocol with reservation. Because for voice transmission, reserving the bandwidth, reserving the time slot is very much important. Hence, D-PRMA is giving us the solution. What is there? Channel is time scheduled and is divided into fixed equal sized frames. That means whatever is the total channel, channel means through which the data transmission is taking place. So channel is having actually time schedule. That is for first 10 seconds, this sender node 1 will transmit. For next 10 seconds, sender node 2 will transmit. Next 10 seconds, sender node 3 will transmit. So the contention is there, but it's a fair contention. So whenever we are using D-PRMA, time scheduling we are doing, in that case, amount of collision will be very less. So that is what is said. Channel is time scheduled. The channel means through which the data transmission takes place between transmitter and receiver, or sender and receiver. So that is time divided, and each frame, there is overall time frame, let's say 10 minutes. Okay, the overall time frame is composed of S slots. So let us say the 10-minute slot is divided into 10 slots. So S is equal to 10. Okay, that means each sender node will get, suppose there are 10 senders, there are 10 minutes time slot. So first sender will send transmission for 1 minute. Next 1 minute, second sender node will catch hold of the channel and send the data to the receiver. So likewise, there is no difficulty. So everybody will get a fair chance to transmit the data. So likewise, each frame means time frame, that means 10 minutes I told you, is again divided into some mini slots. So this whole time frame structure is to be explained if this question is asked. So main question in this case is explain the D-PRMA frame structure. So what are the different frame structure? So each frame is composed of S slots. So total time frame is divided into S slot. Each slot in S again is divided into M number of mini slots, and each mini slot is again divided into two control fields. One is called as RTS BI, another is called as CTS BI. BI stands for busy indication. So if a node has sent a RTS and it is the RTS BI flag is on, that means it has sent the request to the receiver that can I send data. And then after sending RTS, as long as this node is not getting a CTS, till that time the RTS BI flag will be on. Same, what is CTS BI? BI stands for busy indicator. One receiver receives a RTS BI signal from a sender. Okay, so RTS goes from sender to the receiver, CTS comes from receiver to the sender. So after sending the RTS, the transmitter switches on its RTS BI flag till it is not receiving CTS. After receiving RTS, when the receiver finds that yes, channel is free, data can be transmitted from transmitter to the receiver. So receiver has to acknowledge that yes, transmitter, you can transmit data to me. So for the receiver sends a CTS signal back. So when the receiver sends the CTS signal back, at that time the CTS BI flag is on for that receiver. Okay, so let us first see what is the packet structure. So this is the question for all these three protocols that we are going to see. So first we are seeing D-PRMA, second we will be seeing CATA, CATA, and third thing we will see HRMA. Okay, that is hop request, something like that. Okay, so for all these three, the common question for 8 to 10 marks is explain the packet structure of all this contention based protocol with reservation mechanism. So each can be a 10 marks question, and main thing you have to explain is the packet structure. So this is a slide for D-PRMA, and this is the D-PRMA packet structure. So what all things we can find here, just check. This is the total frame length. Okay, so total time slot is, let's say, 10 minutes. 10 minutes have been divided into 10 slots. So each slot is 1 minute, 1 minute, 1 minute. Likewise, there may be 10 slots. Now just check what is there in one slot. Okay, in one slot, it is again divided into m number of mini slots. This is the first mini slot. As soon as this first mini slot starts, the contention starts by all the different sender nodes altogether. So contention or this slot is there just for two things. First, in first mini slot, there is a carrier sensing. So already is there in communication going on that is sensed by all the sensors or all the senders during this period. So whatever is shown here, this yellow, green, pink, gray, all these are time. Okay, so everything is time. So one slot again I have shown separately. So each of the slot is having the same M kind of mini slots. Okay, so one slot I have shown in detail. So what happens in the first mini slot? In first mini slot, two things happen. First is carrier sensing happens, that if there is occurring any kind of already there is a transmission going on in the network or not. If not, then the contention starts. What is meant by contention? All node starts asking for the carrier, and depending on the node health, node characteristic, depending on the contention characteristics, that how important that sender is, how important the data is, MAC allows the channel to one sender initially. So that whole process goes on in the module 1, that is in the first mini slot. So let us go through what is written here. These control fields are used for slot reservation and for overcoming the hidden terminal problem. Okay, so together all these things are actually, why am I slotting? I'm slotting because no two channels should transmit simultaneously. In that case, the hidden terminal problem is solved. What is hidden terminal problem? Two sender node trying to transmit at the same time and trying to catch hold of the receiver. Hence data collision occurs. But if there is this kind of slotting, that is first slot 1, one transmitter will transmit. Next slot 2, another transmitter will transmit. In that case, those collision will not be there. So these control fields are used for slot reservation and for overcoming the hidden terminal problem. So all the slots are there together. They are actually solving the hidden terminal problem. Now let us find out what is there inside one slot. So one slot is again divided into m number of mini slots, and each mini slot is again having two things, RTS-BI and CTS-BI. What is there in RTS-BI time? Whichever sender node has won the contention in the first mini slot. So first mini slot is there for two work. First one is, it is there to sense the carrier. If carrier sensing is done and there is no carrier, then contention will happen. What happens in the contention? All the sender nodes tries to catch hold of the channel, and one of them catches hold of the channel. So what happens? Then it starts transmitting data over the other mini slots. This is what is happening. And in next mini slot, after contention, after winning the contention, what happens? This sender which has won the contention, it will send the RTS-BI, that is request to send, and this is busy indicator, to some receiver somewhere. And that receiver will receive this RTS-BI, and that receiver will send the CTS-BI. And in this slot, the CTS-BI will be received by this sender in module 2. So module 1 and module 2 is mainly for carrier sensing and contention. Contention is won by the sender, then it will send RTS-BI, CTS-BI. So first two slots are there, you are not transmitting any data. So first slot is for carrier sensing and winning the contention. Second slot is for RTS and CTS. Because without RTS, CTS, we cannot transmit data. In that case, again, collision will happen. What happens from third to the M slot? All the data transmission takes place in the third to the M slot. So it is written here, all nodes having packets ready for transmission, contents for the first mini slot, that is module 1. Remaining M-1 slot are granted to the node that wins contention. So contention winning happens in first mini slot. Same slot in each subsequent frame is kept reserved for winning terminal until it completes the packet transmission. So if this module 2, module 3, module M is over, and then also there is some data remaining, so in the third slot the same thing will happen, and the same node will be transmitting data in the third slot also, because it has won the contention. As long as its data is not getting exhausted, it will keep on transmitting. So this is what is the first slide in D-PRMA. Second slide, it is shown as a first slot is kept for carrier sensing. So I told you that first slot is doing two things. First mini slot is sensing the carrier, that is the first thing, and winning the contention. After that RTS CTS, after that all data transmission takes place. So if no node wins the first mini slot, so I told you actually what is D-PRMA frame format. Nothing new is there. Now different cases. If no node wins the first mini slot, that is, nothing happens. All the nodes are trying to catch hold of the media, but none of them won the contention. Then what happens? Then in the second mini slot, again the contention will go on. So if contention is won in the first mini slot, second mini slot is used for RTS CTS. But if contention goes on, okay, if no node wins the contention in the first mini slot, then again contention will go in the second mini slot. If one sender wins the contention at this time, then in the third mini slot, RTS BI and CTS BI will happen. So this is what is said. No node wins contention in the first mini slot, then remaining mini slots are continuously used for contention till a contending node wins a mini slot. Communication within reserved slots takes place by means of TDD, that is time division duplex. This is what is called as time division multiplexing. That means one sender, one receiver transmits at a time. It will never happen that two senders are trying to send data at a time. It will not happen. Okay, so one sender and one receiver will contend for one channel at a time. That is what is called as time division multiplexing. So there is no chance that it will be having any kind of collision. Okay, so communication within reserved slots. So this is a reserved slot. By the winning contention winning node, they will be transmitting data here. So this reserved slot takes place by means of TDD, time division duplex. Duplex means it can receive, it can transmit data at the same time. So that whole channel is blocked by that sender and the receiver module. So it can happen by TDD or it can happen by FDD, that is frequency division duplex. The frequency division multiplexing is also another type of multiplexing. Within that time it will happen. Okay, and it is a duplex communication, that is sender and receiver can both transmit and receive. So any node that wants to send packet has to first reserve slots if the slots is not reserved already. So how can you reserve slot? The slot reservation is occurring by winning the contention. So the very important thing is explaining the first mini slot and second mini slot. First mini slot is for carrier sensing and contention winning. Second mini, if contention is won, second mini slot is for RTS BI and CTS BI. So this is about explanation of frame structure of D-PRMA, that is distributed PRMA. So PRMA is for centralized network like cellular network and all, but we are trying to bring that concept in a distributed manner to the ad hoc wireless network. That's why it is called as D-PRMA. And this is the slot structure. Some more understanding. So this slide looks very big, but already we have explained everything. So certain period at the beginning of the mini slot, it is kept for carrier sensing. If sender node detects an idle channel at the start of the mini slot, it transmits a RTS packet. Okay, the packet is in the slot is in the reservation request. So packet is blocked, the channel is blocked. After that, RTS packet is transmitted. The packet is slot reservation request. The packet is a slot reservation request between the sender and the receiver. This RTS packet is transmitted to the intended destination through RTS BI part of the mini slot. So I told you that after winning the contention, then RTS BI flag will be on as long as the RTS is not reaching to the receiver. On receiving the RTS request packet, the receiver node responds by sending a CTS packet through CTS BI part. So in that part which was shown previously, in this CTS BI, CTS will be received by the receiver. So that is what is said. If sender node receives the CTS successfully, it gets reservation for the current slot and now can use the remaining mini slots till mini slot number M for data transmission. So first contention win, second RTSBI, CTSBI, then third to the M. What will happen is same thing is said, the mini slots till M, data transmission will go on. Now these two are very important. I'll tell you, in order to prioritize the nodes transmitting voice traffic. Now how exactly voice traffic is taking place, transmission is taking place here. So two rules are followed by D-PRMA. The first rule, whenever voice nodes, what is meant by voice node? One node who is transmitting voice signal, that is called voice node. If he starts contending for one mini slot, that is the first mini slot, winning the contention is there happening in the first mini slot. So whenever a voice node or voice message carrying node is asking for the contention, it will be given probability is equal to 1. That means if any sender node is having voice signal, that will be giving probability 1. That means the MAC protocol will ensure that that voice node transmitting sender will be getting huge amount of bandwidth, and that will win the contention. So that's why voice node data or sender will be getting contention is equal to 1, but data node will be given probability less than 1. That means if there are two nodes, both are asking for the first mini slot, both are asking for the channel in the first mini slot time period. If it is a voice node or node with voice data, then it will be given the full contention because it is having probability of 1. If it is data node, that is any sensor data it wants to transmit, then it will be given a less preference. So actually this first rule is deciding who is given most importance and who is given less importance. So we have found that voice nodes are having highest importance, that will be given chance to win the contention and transmits the voice data, whereas simple data node or sensed data is given less contention. So this is because reservation process for voice node is triggered after arrival of the voice traffic at node. This avoids necessary reservation of slots before data comes. So before the data comes, because voice is a real-time data, after the data comes, you start all this process, you will be losing some voice data. So before the voice data comes, as soon as the node knows that yes, voice data will come at this time, before that only the reservation of the channel between sender to the receiver has to be completed. Okay, so after the voice data comes, then all this process goes on. No, before the voice data comes, all this contention, the channel booking between the transmitter to the receiver should happen. So this is the rule number 1. Rule number 2, only when a voice node wins a contention for a mini slot, it is permitted to reserve the same slot in each subsequent frame until the end of the session. But if data node wins the contention, it is allowed only one current slot and it has to make contention for subsequent slot. Let's see this slot characteristic once, what is meant by that. If let's say a voice node has one contention here in the second slot. So in the second slot, voice node has one contention. Then it will be transmitting data for all M. Okay. Then in next session, again automatically the voice node will not have to win a contention. That is what is meant there. Okay. So if it is a voice node, it has won the contention, it will transmit all its data in slot 2. Again, when it goes to slot 3, if it is a voice node, this whole thing will be booked for it already. Okay, so and it will transmit data. In 4th slot, again the whole thing will be booked for it already, and it will be sending the data if it is voice node. But if it is data node, first it has to win the contention here, transmits data. Then comes slot 3. Slot 3 is also having this kind of packet structure. Here in slot 3, again the voice node has to win a contention. Okay, so this is the difference. If it is a voice node, then once it wins the contention, it will keep on going as long as the voice data transmission is not completed. But it's a data node, every time in every slot it has to win a contention. So data node has one contention here and will be transmit. In the 3rd slot, again if it's a data node, again it has to fight, again win contention, again go on, because data is less important. That's why it is said here, only when a voice node wins a contention for a mini slot, it is permitted to reserve the same slot at each subsequent frame. That means in slot 2 it has won the contention, slot 3, slot 4, slot 5, continuously the voice node can transmit data until the end of the session. But if data node wins the contention, then it is allowed only for that current slot. So data node wins contention here in slot 2, in slot 3, that data node will not be given automatic choice. Again in slot 3 it has to win contention and then transmit data. Because data node is less given less importance, voice node is given more importance. I'll not be explaining all this in detail. It is D-PRMA is doing what? D-PRMA is actually avoiding packet collision because all the slots and everything is set there. So it is using actually time division multiplexing. So there is no packet collision. Exposed node can transmit simultaneously with the transmitter. So if N1R1 is making a pair with this kind of D-PRMA protocol, then if there is another node N3 which is an exposed terminal, it can also make another pair with R2. So with not with the same receiver, but with another receiver, it can make a pair. So when N1R1 communication is going on, at that time, N3R2 communication can go on simultaneously. So this solves the hidden and exposed terminal problem. So there is no collision, means no two sender are asking for same receiver. It cannot happen because there is a time scheduling. So two sender nodes asking for one receiver does not happen because of time scheduling. This actually solves the hidden terminal problem. And what is meant by exposed terminal? That when one N1 R1 is made a couple, then N3 actually is not getting a slot. Okay, that will not happen because N1 R1 is made a couple, then N3 R2 also will be making another couple, and that will not disturb the N1 R1 communication. So these two are very important. So in MACA, this problem was there, problem of hidden terminal and exposed terminal. MACA W had solved it. So there is a very important question that how MACA W solves the hidden terminal and exposed terminal problem of MACA. So first you have to explain what is MACA, what are the problems of hidden terminal and exposed terminal problem in MACA, and then how MACA W solves it. This is a 10-mark question. This D-PRMA is automatically solving the hidden and exposed terminal problem. How hidden terminal problem is solved? Through scheduling. How exposed terminal problem is solved? Exposed nodes can transmit simultaneously with the transmitter, provided that exposed node is not within the radio range of the receiver. Okay, so the exposed node N3 should not be in the range of R1. So N1 R1 will be transmitting in one side, N3 R2 will be transmitting in another side. So that is not a problem. One more thing, solution of the exposed terminal problem: an exposed node which hears RTS but not hears CTS is allowed to transmit simultaneously. So an exposed node is hearing RTS but not hearing CTS. Means what? That exposed node N3 is within the range of N1 but not within the range of R1. So this one diagram I gave in the 8th lecture of hidden and exposed terminal, वो तुम्हारे दिमाग में होना ही चाहिए. Okay, so N3 is within the range of N1. Hence, whatever RTS is sent by N1, N3 can listen to that. But N3 exposed node is not within the range of R1. Hence, CTS, whatever is sent by R1, will not be heard by the N3. So thus exposed node problem is solved. If RTS CTS packets collide and a successful reservation cannot be made in mini slot 1, then subsequent mini slots are used for contention purpose. This is what is explained in the previous thing. If module 1, this first mini slot is not giving any result of contention for some sender, then what has happened is in module 2 still the contention will go on. So this is what is said, RTS CTS packets. So there are many senders, many receivers. Okay, so RTS from one sender collides with the CTS from another receiver. Okay, if that collides, then both packets are lost. Then communication couple R1C1, N1 R1 or N2 R2 is not possible. In that case, again a new RTS CTS packet has to be exchanged between few couples, and then only they can make a pair and they can transmit. So if it cannot happen in the first mini slot, next mini slot it can happen. CTS BI packet by the receiver eliminates the hidden terminal problem. Okay, because CTS signal is very important. Whenever CTS signal is sent by some receiver, means what? That receiver and that transmitter from where the RTS signal came, they are making a couple. So in our case, R1 and N1, they are making a couple. So whatever CTS signal is sent by that R1, okay, it goes to the another hidden terminal N2 also. So though N2 is a hidden terminal, though N2 wanted to transmit to R1, but just listening to this CTS BI, which is for N1, N2 will understand that yes, I should not transmit because N1 and R1 is trying to make a couple. So in that case, the N2 will stop its transmission, L2 will not contend for R1. Finally, after successful data transmission, if a node does not want to keep the slot, it stops sending BI signal. So as long as one sender and receiver node is using this whole module 1, module 2 up to module M, suppose after module 5, all the data from this sender is over. So as long as this communication is not getting over, BI signal will be on. BI signal means busy indicator. So as long as this sender and this receiver, some receiver, they will be keeping the channel, this BI flag will be on. So after the data transmission is over, so finally after the successful data transmission, if a node, a sender node does not want to keep the channel, then it stops sending the BI signal. So it stops sending BI signal means D-PRMA is more suitable for voice traffic. So its communication is done, then BI signal will be switched off. As soon as switched off, the receiver and transmitter will not get linked up anymore. So in that case, some other sender can be given the contention of that channel. Okay. So this is all about D-PRMA protocol. Remaining two protocols we will do little fast. Okay, so I'll be taking it up to 3:30. So please give me some time, 10-15 minutes. Okay. So next is CATA protocol. What is CATA? It is called Collision Avoidance Time Allocation Protocol. Okay, so it depends on the dynamic topology, depends on nodes content to reserve the time slot. Same thing, whatever happened in the previous case, that some transmission receiving node, they were giving some kind of time slot, and that sender receiver node were transmitting in that time slot. It supports unicast, broadcast, and multicast transmission simultaneously. Now these three things are to be known. Very important question: what is meant by unicast, what is meant by broadcast, and what is meant by multicast? Unicast means one sender to one receiver. Broadcast means one sender to many receiver. So whatever happens in case of TV transmission, it is called broadcast. Okay, unicast means one sender to one receiver. So whatever is happening now, none of you are talking, so actually it is broadcast. What is meant by multicast? Many sender to many receiver. So these are the three things. I'll repeat. Unicast means one sender to one receiver. Broadcast means one sender to many receiver, and multicast means many transmitter to many receiver. CATA protocol actually is collision avoidance. Whenever I am saying collision avoidance means this is using some kind of time scheduling, okay, and time allocation protocol. So whatever is done in D-PRMA, same kind of thing is being done in CATA, but in a different way, because CATA is having a different packet structure. That's all. Okay, it supports broadcast, unicast, multicast transmission separately. There are two principles. First principle is easy to understand. It says that the receivers of flow must inform the potential source node about the reserve slot. So receiver should tell the transmitter that yes, the channel is open, you can transmit to me if the channel is open. Similarly, the source node must inform the potential destination nodes about interferences in the slot. So this CATA is actually having a global essence. The receivers are sending, continuously receiving data from three channels, and receiver is continuously telling all these three nodes that yes, you can send me the packets because the path is clear. Simultaneously, if there are any nodes who is experiencing there is a collision, there is a congestion in its path, that receiver, that transmitter will continuously tell the receiver, no, the path between you and me is blocked, so there is a congestion. So this first thing is very important. Receivers of a flow, that means continuously packet transmission is going on. From the potential source, it keeps on telling the source that these are the path through which packet can be received. So receiver or the receivers of a flow must inform the potential source node about the reserve slot, whereas the source node must inform the potential destination node about the interference in the slot. Interference means congestion. This is the first rule. Second rule is usage of negative acknowledgement. What is meant by negative acknowledgement? It is called as NTS, do not transmit. Okay, so this was not there in previous case. If one receiver is busy with another transmitter, so N1, R1, they have made a couple and they are transmitting. In that case, the R1 receiver will continuously transmit a NTS signal. What is that NTS? It is called as don't transmit. Okay, not to transmit. That NTS signal will propagate to all the sender nodes in the network, so that all the sender nodes will understand that yes, this receiver is blocked with some kind of other sender, so other senders will not transmit any kind of signal for that receiver. So this NTS signal, or not to send is actually transmitted by a receiver, okay, for the other transmitters who are trying to catch hold of that receiver. Okay, so not to send is actually called as a negative acknowledgement. This is a special feature of CATA. Okay, and control packet transmission, so usage of negative acknowledgement for reservation request and control packet transmission at the start of each slot to distribute the slot reservation information to senders of broadcast or multicast session. Okay, now just check what is the frame structure. So slot 1 up to slot S is the same. So previously here was mini slot 1, mini slot 2, mini slot 3, mini slot 4. In this case, CATA, the main question is what are the meaning of all these 5 things: CMS1, CMS2, CMS3, CMS4 and DMS. So this is the main question. You can write down that in case of CATA frame format, what is meant by CMS1 to CMS4 and what is meant by DMS. Okay, so each sender receiver is line is given one slot. So in the first slot, sender 1 to receiver 1, second slot, sender 2 to receiver 2, third slot, sender 3 to receiver 3. But that does not happen automatically. Each sender has to win that contention. Okay, not necessary that in first sender 1 to sender 2, second sender 2 to sender receiver 2, third sender 3 to receiver 3. No, it's not that easy. Okay, it will happen as per contention. So whichever sender and receiver they win the contention, they transmit. So what is CMS1, CMS2, CMS3, CMS4 and DMS? This much thing we will know. What is meant by CMS1? Okay, so CMS stands for control mini slots. So there are 4 control mini slot and there is 1 data mini slot. So DMS is very easy. In data mini slot, the data transmission happens. So out of 5 things, 1 thing is done. So DMS means data mini slot. In that data mini slot, the data transmission happens. And CMSs are very small, DMS is very big, because control packet size is very small and data packet size is very big. So CMS 1, 2, 3, 4, what happens in that? So it is written DMS is much longer than CMS. Control packets are much smaller than data packets. Hence CMS 1, CMS 2, 3, 4, they are control packets, they are small, and DMS is very big. Each node that receives data. So just you have to assume that there is one DMS here. Okay, so previous thing, it is already sending data. Then what happens in the next slot? So slot 1 DMS is activated, slot 1 data transmission is going on. Then what happens? So what happens is each node that is receiving data during DMS or current slot transmit a slot reservation packet. So what happens is CMS1, so this DMS will send a slot reservation thing, and that slot reservation packet will be received by the CMS1 of the next slot. So here, whatever DMS is there, in this case, that will send a slot reservation, because this slot 2 wants to reserve slot 3. So during DMS 1, a slot reserve RS packet will be sent, and that will be received at CMS 1 of the third slot. So what is CMS 1 used for? CMS 1 is used for packet reservation through a SR packet from the previous slot DMS. So each node that receiving data during DMS of current slot transmit a slot reservation packet during the CMS 1 of the next slot. So this DMS will send the SR, and that will be received by the CMS 1 of the next slot. So what is CMS 1 used for? It is actually, this informs the potential neighboring nodes about currently active reservation. The SR packet, when received at the neighboring nodes, prevents the neighbor nodes to attempt to reserve the current slot. That means this communication is going on. DMS send the SR packet for the next CMS, because whatever sender is there in slot 2, that wants to book the slot 3 as well. Okay, in that case, the DMS of slot 2 will send a SR packet for CMS 1 of slot 3. This is the job of CMS. So what is the job of CMS? It actually receives the slot reservation packet from the previous transmission. What happens in CMS2? So CMS2 means next CMS2. Every node that transmit data during DMS of the current slot transmit RTS packet during CMS of the next slot. So during CMS, actually the RTS packet is transmitted. What happens in CMS3? CMS3, the CTS packet is received by the slot. So this current slot communication is going on. Okay, so first RS will be sent, it will be received by the CMS1 of the next slot. Then comes CMS2. CMS2 will send the RTS. What happens in the CMS3? CMS3, the CTS packet is received. And what happens in the CMS4? So when RTS CTS communication goes on and RTS CTS communication is completed, it means that one sender and one receiver has blocked that time slot. So when RTS CTS is helping to block that time slot, in that case, for an already reserved channel, so for an already reserved channel means RTS CTS exchange has happened through CMS2 and CMS3. Then during CMS4, so this is very important, then during CMS4, the current sender node transmits NTS not to send. Okay, so when the RTS CTS exchange is done, the sender node has blocked the receiver node, then the sender node will transmit a negative acknowledgement, which is a special feature of CATA. So not to send packet will be sent, which is a negative acknowledgement. When an exposed sender node, so other sender nodes, when they receive this kind of NTS thing, they will understand that one sender has booked another receiver. Then we are not supposed to transmit. So when an exposed sender node receives NTS during CMS4, it understands that its reservation request is failed and it does not transmit along DMS of the current slot. So if I asked what is happening in the CMS1, so CMS1 is actually for slot reservation. Okay, so this is a request kind of. So before RTS, it's a slot reservation thing happening in the CMS1. So DMS send the SR packet and it is received by the CMS1 of the next slot here. What happens in the CMS2? After receiving the slot request, this in CMS2, RTS signal is sent from the sender to the receiver. In CMS3, the receiver sends the CTS back and that CTS is received in the CMS3 in the CMS3 slot. Okay, by the receiver in the, so receiver sends the CTS, so that CTS is received by the transmitter in the CMS3 slot. After RTS CTS exchange takes place, that means this node has got the reservation for the receiver. Then that transmitting node will send a NTS signal in CMS4. That means that sender will tell all other senders that the channel is now blocked, you please don't transmit. So listening to the NTS signal from the contention waning sender, other sender nodes will stop their transmission. They will not be sending anything. So after the channel is blocked, after channel request, channel is blocked, then other nodes are told not to transmit. The whole path is clear. Now the communication, data communication will go on from the transmitter to the receiver in the DMS block. And DMS block is very long, CMS block is very short. So this is what is CMS1, CMS2, CMS3 and CMS4. These are some of the data about CATA protocol. If you want, you can go through, okay, at your sweet time. And the same thing is given in the book also, so don't worry. Last, in a very short time, we will do another thing which is called as HRMA protocol. So what is HRMA protocol? So main thing in this case is D-PRMA. So D-PRMA is sure short a 10-mark question. What is a CATA? In CATA, the question asked is the 5 packets, CMS1 to CMS4 and DMS. What is the job of that? In HRMA also, the slot structure can be asked, and it is not a 10-mark question because it is not very big. So HRMA is mainly asked for 5 to 6 marks question. So this is also a reservation kind of a thing, but more than time reservation, this is a frequency reservation, or this is a hop reservation multiple access. So you are definitely studying what is meant by hop reservation in mobile communication. Okay, so in this, HRMA is a multi-channel MAC protocol. So all these are MAC protocol. They are actually managing the channel when many senders and many receivers are there. So when there is many requests at that time, how the MAC protocol managing the channel over all these senders and receivers, how the bandwidth is managed, all these things are done by the MAC protocol. So this is HRMA is also a MAC protocol. It is called hop reservation. What is that? This is simple half duplex. What do you mean by simple half duplex? In half duplex, you can talk or you can listen not simultaneously. So whenever you are talking, somebody else is listening. Whenever the receiver is talking, you are listening. So this is not, so full duplex is anytime anybody can talk and receive. Half duplex means either you talk or you receive. So one thing. And next is frequency hopping spread spectrum. So you know what is spread spectrum. You're already doing mobile communication. Okay, so here it is frequency hopping type of spread spectrum. So a certain frequency bandwidth is allocated for every node for transmission from transmitter to the receiver. So it is kind of a frequency division multiplexing. So in time division multiplexing, what we are doing is we are keeping a time slot, okay, for a node to transmit and receive the data at the receiver side. In frequency hopping, we are keeping a frequency slot, okay. So even if simultaneously 3-4 different nodes are transmitting, but all these different nodes are transmitting with different frequency bands. Hence, even if they are concurrent, even if they are transmitting at the same time, but they are transmitting with a different frequency. Hence, the frequency mixture or data mixture or collision will not happen. So whatever is the transmitting frequency, receiver knows that. So receiver will be receiving data only at that frequency. So you can check here what is the packet structure. So it is slot 1, slot 2, slot 3 up to slot M. Okay, but here there is a synchronizing slot. So all the nodes are synchronized first. So it uses reservation and handshake mechanism to enable a pair of communicating nodes to the receiver to reserve a frequency hop, and thus ensuring collision-free data transmission even in the presence of the hidden terminal. So even if the hidden terminal is transmitting data, but its whole frequency range of transmission is different than the sender node. So N1 and N2 both are transmitting with different frequencies. Hence, their data will not get entangled, so collision is avoided. So it can be viewed as a time slot reservation protocol. So different slots is given, and at every time slot, the sender is sending data with a different frequency. So that is what is HRMA. So in one word or in one line, if you want to say, it is slots are defined for every transmitter receiver, and in every time slot, the transmitter and receiver is transmitting and receiving over a different frequency bandwidth. Okay, so that's why there is no chance of signal collision. So it can be viewed as a time slot reservation protocol where each time slot is assigned a separate frequency channel. So slot 1, maybe it is using 1000 megahertz, slot 2 maybe 1500 megahertz, slot 3 maybe 2000 megahertz. Likewise, it is occurring. So senders and receivers, they are different in time, they are different in frequency. So out of L frequency channels, so let's say there are L number of sender and L number of receiver, hence there are L number of channel. Okay, so they are actually having one special bandwidth which is called F0. Out of F0, that F0 frequency band is used just for synchronizing all the things. So this is this L frequency channels. HRMA uses one frequency channel, if not as dedicated for synchronizing channel. So nodes exchange all the synchronized sync bits. Okay, so for synchronizing all the channels, one bandwidth is used. So all the node data are exchanged, that I am here, you are there, this is my timing, that is your timing. So initially, just before transmission occurs, all the synchronization happens over that frequency, if not among all the nodes and receivers, and then starts the transmission. What are all this? So first thing, every slot is also having a sync bit, and every slot is having a hop reservation. So here the hop reservation is happening, that selecting the slot and contending for the slot and winning the slot and booking the slot. That happens here. And after the slot is booked, the RTS and CTS is ensuring that yes, slot is booked, and remaining time actually the data transmission takes place. So all these things are said in HRMA. Time is slotted, and each time slot is assigned a separate frequency hop, which is among M hop frequencies. So here time separation is also there, frequency separation is also there. So each time slot is divided into 4 slots: synchronous, hop reservation, RTS and CTS. So synchronous is for data exchange among all the sensor nodes. HR, that is the hop request, is to book the channel. RTS and CTS is completing the channel booking. So during the synchronization period of each slot, all idle nodes hop to the synchronizing frequency, if not to exchange sync information. Last slide, data packets transmitted can be of any size. Data transmission can take place through a single packet or through train of packets. So after all these initial things are over, then the data transmission happens. A maximum dual period is defined to prevent nodes from hogging onto a particular frequency channel. So it should not happen that one node is getting all the channel access throughout. Okay, so that is called as hogging. It will not happen. The MAC protocol ensures that not a single channel takes all the time. Okay, so all the sender nodes, all the receiver nodes will be getting time in a rotational manner. So one sender, one receiver, their communication done, then another sender, another receiver. So all these things actually are ensured by the MAC protocol. Last line, transmission of data packet should not be larger than this maximum dwell period. So whatever is the total width of the data packet, that should be less than the dwelling period. That means every communication link has to complete its transmission within the dwell period. Okay, so these are the three protocols which is called as contention based protocol with reservation mechanism. So that almost finishes this chapter.